Welcome students. In previous class we discussed VSEPR theory and limitations of VSEPR theory. Today we will discuss hybridization and shapes of different molecules. The concept of hybridization was propagated by Pauling and Slater. Hybridization is the process of mixing of atomic orbitals and formation of new orbitals of equal energy is known as hybridization. And the new orbitals formed are known as hybrid orbitals. In a simple word, we can say that phenomenon of mixing of atomic orbitals and formation of new orbitals is known as hybridization. The bond formed by such orbitals are called hybrid orbitals. And the compounds which results in from these bonds are known as hybrids. There are different rules for hybridization. First rule is only orbitals of similar energies belonging to the same atom or ion can undergo hybridization. A number of hybrid orbitals produced is equal to the number of orbitals mixed. Hybrid bonds are stronger than the single non-hybridized bond of comparable energy. And third rule is most of the hybrid orbitals are similar, but they are not necessarily identical in shape. They differ from one another in orientation in space. Next is for equivalent hybrid, the orientation in space is determined by the number of orbitals mixed and consequently the number of hybrids obtained. And which of x, y and z directions are preferred by the orbitals when pure. The type of hybridization indicates the geometry of molecules, and from the type of hybridization we can tell about the bond angles and structure. Once an orbital has been used to build a hybrid, it is then no longer available to hold electrons in its pure form. And during hybridization, only degenerate orbitals involved in hybridization. And the extent of overlapping of the hybrid orbital is greater than only hybrid orbitals. Hybrid orbitals possess lower energy and they form stronger bonds. There are different types of hybridization. Hybridization of sp type, hybridization of sp2 type, hybridization of sp3 type, hybridization of sp3d type, sp3d2 type, sp3d2 and d3 type. And these are the types of hybridization. We will discuss one by one. Hybridization of sp type. A linear combination of one s and one p orbital yields two sp hybrid orbitals. And this mixing of orbital is known as sp hybridization. Two sp hybrid orbitals are completely equivalent in energy and each sp hybrid orbital is stronger than the pure s and pure p orbital from which it is formed after hybridization. In sp hybrid orbital, there is one large lobe and one small lobe. The large lobe, which is much bigger than the p orbital, bring about a higher degree of overlapping with the orbital of reacting atom. Thus, the resultant bond is comparatively stronger. Each sp orbital has one half s character and 1/2 p character. It means 50% s character and it has 50% p character. Now let us see the example of sp hybridization or geometry of barium fluoride. Barium difluoride. An example involving sp hybridization is beryllium fluoride. In beryllium fluoride, the beryllium atom is not in the ground state, but it is in the excited state with sufficient extra energy to unpair a 2s electron. Let me write in the ground electronic configuration of beryllium. This is 1s, 2s, 2, p, 1, 1s, 2, 2s2. This is the electronic configuration of beryllium in the ground state. In the ground state. And in the excited state, it would be one s2, 2s1 and 2p1, and beryllium atom in beryllium fluoride. This would be 1s2, 2s2 and 2p. S hybridization is sp. Hybridization. And angle is 180. As there are two unpaired electrons in an excited state, so beryllium can form two bonds in beryllium fluoride by gaining two electrons from two fluorine atoms. Beryllium fluoride involves 1s and 1p orbital. It means that these two bonds should be of different strength, and since s orbital is non-directional, the bond angle cannot be predicted. In fact, the two bonds are of equal strength and molecule is linear with the bond angle. That is, a bond angle is 180 degree. And this can be explained by the hybridization. The energy of the s and p orbital is combined and the two hybrid orbitals of the same shape and energy are formed. That you can see in this picture. In beryllium fluoride, the two hybrid orbitals must lie as far apart from each other as possible in order to minimize the force of repulsion, and thus they have a stable structure. And the molecule therefore will be linear and the bond angle will be equal to 180 degree. So the hybridization in beryllium fluoride explains that two bonds are of equal strength and the shape of this molecule is linear. Let us see in sp2 hybridization or the formation of sp hybridization. sp2 hybridization, actually the combination of 1s and 2p orbitals to form three orbitals of equal energy is known as sp2 hybridization. And these three bonds are coplanar and directed at an angle of 120 degree to each other. All the three sp2 hybrid orbitals are completely equivalent in energy and shape, and the relative overlapping power of each hybrid orbital is 1.99, that is calculated value. And all the three sp2 hybrids lie in the plane of p orbital, and they are oriented at 120 degrees with respect to each other. And sp2 hybrid orbital has 1/3 s character and 2/3 p character. That means that it has deduced that the ratio of p character to s character is 2:1 in sp2 hybrid orbitals. For example, or we can see the as such type of hybridization in beryllium trifluoride, boron trifluoride. The boron atom is the central atom in boron trifluoride and has the electronic structure is 1s2, 2s2 and 2p1. The atom in its ground state has only one unpaired electron, so that it can form only one covalent bond, but in the excited state, this is the ground state of boron, 1s2, 2s2 and 2p1. In excited state, it is 1s and p. And the boron atom in boron trifluoride boron atom in boron trifluoride after gaining electrons. Boron atom in boron, that would be 1s2, 2 and in p orbital it is. So here hybridization is sp2. In excited state, there are 3 unpaired electrons and hence 3 bonds can be formed. The 3 orbitals 1s and 2p used for bonding do not represent their original characteristics, but are hybridized to produce the 3 sp2 hybrid orbitals. The 3 bonds are equivalent and are 120 degrees apart, and the shape of the molecule is therefore triangular and planar in sp2 hybridization. According to Sedgwick and Paul theory, the 3 sp2 hybrid orbital should be an angle of 120 degrees to each other. And this arrangement would result in the falling of force of repulsion between electron pairs to minimum value, as 3 sp2 hybrid orbitals overlap with orbitals of 3 atoms. That means each fluorine, the bond between the fluorine and boron angle would be equal to 120 degree, and hence the molecule will be triangular, as you can see in this picture. And now sp3 hybridization. sp3 hybridization is the mixing of 3p and 1s orbital to form 4 orbitals of equal energy. In sp3 hybridization, 1s and 3p orbitals of almost same energy intermix to give 4 identical and degenerate orbitals. And these, the 4 sp3 hybrids are directed towards the 4 corners of the regular tetrahedron, whose center is occupied by an atom that has undergone hybridization. And these 4 hybrid orbits orient themselves with an angle of 109 degree 28 minutes between them and point to the 4 corners of regular tetrahedron. Typical example involving sp3 hybridization is the shape of methane molecule. In this case, carbon, the central atom, is and has only one unpaired electrons in the ground state. In the excited state, 4 unpaired electrons are available for bonding, and the 4 bonds so formed are not of equal strength, but actually they should be of equal strength. And in order to explain 1s and 3p orbitals undergo hybridization, and 4 equivalent sp3 hybrid orbitals are formed, and these 4 hybrid orbitals can form 4 covalent bonds with hydrogen atom to give a molecule of methane. And according to Sedgwick and Paul theory, the repulsion between 4 orbitals is smallest, and they point to the corner of regular tetrahedron and make a bond angle of 109 degree 28 minute. And the carbon atom is at the center of tetrahedron and 4 hydrogen atoms are at the corners. Now next is sp3 dehybridization. In sp3 dehybridization, 1s, 3p and 1d orbitals of same energy intermix to give 5 identical and degenerate hybrid orbitals. And all these 5 hybrid orbitals are not of the same type, but they can be divided into 2 non-equivalent sets. First set consists of 3 equivalent hybrid orbitals which are oriented in a plane towards the corner of triangle. And this set is known as equatorial set of orbitals, in which the hybrid orbitals are inclined at 120 degree to each other. And the second set is known as axial set, which consists of 2 equivalent hybrids obtained by mixing one pz and one dz to dz square orbitals. The hybrids of these set make an angle of 180 degree to each other. But with the hybrids situated in the triangular plane, they make an angle of 90 degree. An interesting example involving sp3 dehybridization is provided by PCl5. And the electronic configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, that you can see in this picture. The phosphorus in its ground state has only 3 unpaired electrons. In order to explain the formation of PCl5, 5 unpaired electrons are required, and it can be achieved by the unpairing of electrons in the 3s orbital by the excitation of the atom. And these 5 electrons, 1s, 3p and 1d, undergo hybridization to 5 hybrid orbitals. And these 5 hybrid orbitals combined with 5 chlorine atoms to give phosphorus pentachloride. Thus the phosphorus pentachloride has trigonal bipyramidal structure or symmetry. The structure is not symmetrical one and hence unstable. Thus PCl5 is highly reactive and is split into PCl4 plus and PCl5 ions in the solid state, which have tetrahedral and octahedral structure respectively. Now, sp3d2 hybridization. In sp3d2 hybridization, 1s and 3p and 2d orbitals of same or different shell mix to give 6 sp3d2 hybrid orbitals, or the mixing of 1s, 3p and 2d orbitals to form 6 orbitals of equal energy, that is known as sp3d2 hybridization, and all the 6 hybrid orbitals in is equal energy. An interesting example is sulfur hexafluoride. The atomic number of sulfur is 16 and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4. As sulfur atom has 2 unpaired electrons in 3p orbitals, it means that it should combine with 2 fluorine atoms to form sulfur difluoride, but it forms sulfur hexafluoride. So, in order to explain its formation, it is assumed that the 2 paired electrons from 3s and 3p become unpaired and get excited to the vacant 3d orbitals by absorbing energy. And now 6 unpaired electrons are available which undergo sp3d2 hybridization, forming 6 hybrid orbitals, which overlap 6 unpaired p to z orbitals of 6 fluorine atoms and form sulfur hexafluoride. Let me write here electronic configuration of in ground state. In ground state, it is 1s2, 3p, 1, 2, 3, 4, and 3d orbitals. 3d orbitals is vacant here, and in excited state, it is 1, 2, 3, and it would transfer into d orbital. And sulfur atom having gained 6 electrons from fluorine atom, then it would be 2, because its spin should be opposite in sign. Then d orbital, 2, 3, 4, 5 orbitals in d section. What do we observe here? sp3, sp3 and d2, sp and 3. 1s, 3p and 2d orbitals are involved in the mixing of hybridization. In sulfur hexafluoride, the 6 hybrid orbitals are directed towards the 6 corners of regular octahedron, and the shape of the sp3d2 hybridization is octahedron.